So hello everyone. Today we're going to be looking at some word problems, but I want to start with one little concept that I was a little concerned about. It was going to happen in one of the homework questions that I gave recently. I did not look at it in class because I wanted it to be a little bit of a challenge when it happened. So if I do something like this. Okay, and I asked you to solve for x. Here's what's going to happen because we have to follow SOHCAHTOA. It's a right angle triangle, right? My opposite side, I'm hoping everybody's getting comfortable with figuring out the opposites and the adjacents and the hypotenuses at this point, since this is review from grade 10. So we've got opposite and adjacent, which means I'd be using TOA from SOHCAHTOA. And if I set up the equation, I have tan 50 is equal to my opposite, which is 10, over my adjacent, which is x. And there was at least one question. It's actually, unfortunately, I think it was the question that had a mistake in the book, but it was at least one question in the homework where that would have happened. And I have seen students that have I don't know, innate fear of putting variables on the bottom. And I mean, that fear is not completely what was the word I'm looking for? It's a good fear to have, but it doesn't mean that it can't happen. So I've had students like just flip this around because it's like, oh, x can't be on the bottom, let's put the 10 on the bottom. No, you have to follow the formula. The formula says opposite over adjacent. You can't flip that around, okay? So what would happen in a case where you have x on the bottom? And I've seen so many mistakes being made. I've seen the 10 moved over and multiplied by tan 50. I don't know why, but I've seen that mistake made often. The issue is x being in the denominator of a fraction is, and we saw that a little bit recently with our rationals. It's like the worst possible place that you can have an x value. Now this is an equation, it's not just simplifying, so we want to get x all by itself. And that is exactly correct. Now I'm going to show all of the math. Somebody suggested the correct way we're going to do this in chat, but I'm going to show all of the math here just to be absolutely sure that you get a chance to see this one more time. If the x is on the bottom, and this is an equation, what you want to do is you want to move the x over to the other side. And if the x is dividing on this side, it means it's going to multiply over here. And as soon as you do that, then to isolate the x, you have to get rid of the tan. Well, where does the tan go? The tan is multiplying on this side. That means it's going to come over here and divide. And yes, you're going to end up dividing by tan 50. So it's not always a multiplication of the number times tan, sine, or cos. You have to still follow the regular algebra. And as was suggested in chat, that means that all that happens is really these two things swap places. Right? Now that's a trick. You have to understand how that trick works. And you could do the multiplication and division all in your head at once. But as long as you remember, there's actual math going on here. Okay, don't just think that I can switch those two things willy-nilly whenever I feel like it. It's because specifically we're isolating x, and x is a denominator. So you will sometimes have to divide by your sine, cos, or tan, depending on where your variable ends up. So I just wanted to discuss that quickly before we start today, because just because I know that a lot of students have struggled with it in the past. So I want to look at a few word problems with you today, working our way up to what I feel is one of the most difficult word problems in basic trigonometry. Now, when I say basic trigonometry, I mean right angle triangle trigonometry. When we get into the sine law and cosine law, and we will be reviewing those, things are going to get a little bit more tricky this year because we're going to be working with angles that are greater than 90 degrees, and we're going to have to see how those get affected in higher level trigonometry. But for right now, we're just doing right angle triangle, trig. And when you read word problems in math, they say that reading math word problems is like one of the most complicated English things you can possibly do, because there's so much information that's shoved into the words, and you have to understand not only the the words themselves, like what you're asked to do, but you have to understand all the math concepts that are in the words too. So I just wanted to take a couple of seconds before we start looking at some of these word problems to remind you of two words that come into play when you're dealing with trig word problems, and that is depression and elevation. So if I say angle of elevation, what I mean is, and this is the way I usually describe it to students, if you're looking out horizontally and you want to look at the top of a tree, do you tilt your head up or do you tilt your head down? And you're going to tilt your head up. Well, the angle that your nose sweeps through as you look up is the angle of elevation. The reverse of that is if you're on a cliff like this little gentleman here is, okay, and you see a boat down below, if you're looking out horizontally, which way are you going to tilt your head? You're obviously going to tilt it down, and the angle your nose sweeps through as you look down is going to be the angle of depression. And I'm sitting here like tilting my head up and down. You can't see me, but anyway. So you have to be very, very careful, because if they tell you, like, and I'm going to give you an example right now. If I told you the angle of depression from the helicopter to the person on the cliff is 30 degrees, could you draw that angle of depression in the right spot? Now I'm going to add 2 dotted lines here. And I'm going to ask the question, is the angle of depression between the green line and the blue dotted line, or is the angle of depression between the pink line and the blue dotted line? And I'd like to see your answers, either green or pink, please. I've got one answer. Is the angle of depression between the pink dotted line and the blue dotted line, or is it between the green dotted line and the blue dotted line? And I'm talking about this dotted line here, the blue dotted line. So we've got 2 pinks, and the pinks are going to win because you are correct. That is where the angle of depression is. The angle of depression, and I can't tell you again how often students will get this wrong. An angle of depression is tilting downwards from somewhere, not tilting upwards from somewhere, right? So it has to be from the pink line going to that blue dotted line, sorry. So let's look at an example of this. And I actually went back to your grade 10 textbook for this first example. A searchlight is mounted at the front of a helicopter. It is 150 meters above the ground. The angle of depression of the beam is 70 degrees. The beam spreads out at an angle of 5 degrees. What is the diameter of the circle formed by the beam on the ground? Now, I would actually call this a more complex basic trigonometry word problem. It is a little bit more complex because really, really basic trig problems are like you're flying a kite, the string is out a certain distance, and they give you an angle and they want to know the height of the kite, which is just basically a right angle triangle. So those ones are very simple to do, and I would assume, having come through grade 10, that you'd be able to do those again. However, this one is a little bit more complex. There's a lot going on in this question. The first one being, they ask you what the angle, or where the, sorry, let me repeat that. They're giving you the angle of depression of the beam. Do you know where to draw it? Okay, and that's what I was kind of preparing you for on the previous slide. So we want to know how the beam spreads out at the bottom. So I redrew the picture here just to be able to label it a little bit cleaner, okay? The beam's right here. It's spreading out at 5 degrees, so I hope you can all see that. The height of the helicopter is 150 degrees. Now, adding in the lines for the right angle triangle is key here, right? If you look up here, you don't see right away, oops, sorry, that right angle triangle here, but as soon as you start to draw it in, right? Then you'll see that right angle triangle. But we're trying to find x, and the problem here is that x is not even in a right angle triangle. Now at the moment, and I know you've gone through sine law and cosine law, but at the moment I'm restricting you to only using SOHCAHTOA and Pythagorean theorem, okay? So only right angle triangle stuff. So at the moment, we don't know how to find x, and even if you tried to use sine and cosine law at the moment, you wouldn't be able to because you don't have any lengths given in that weird triangle, okay? So we need to come up with a plan of attack. Now, generally speaking, folks, if you have a shared side between two triangles in a picture, oftentimes that shared side is going to be like one of the key aspects of solving this problem. Now, I'm not sure if this case is going to require it, but we'll talk about it in a second, okay? But there's actually two shared sides in this picture. This side length here, which is the hypotenuse of this right angle triangle here, I'm hoping everybody can see that side, it's shared between the weird looking triangle and the right angle triangle. But there's another shared side. This side here is shared by both that right angle triangle and the bigger right angle triangle. And since I'm forcing you to work with just right angle triangles here, those are the two right angle triangles I want you visualizing, okay? So both this side is 150 and this side is 150, right? So the 5 degrees is where? Well, the 5 degrees is here, but it doesn't cover that whole angle. It's just like a little sliver of that angle. So the 5 degrees is going to help us, but not right now. We need to do a little bit of work to figure this out. And the first thing we're going to do is talk about the angle of depression. So as I said in the previous slide, the angle of depression is always measured from a horizontal line. And then you're either tilting your head up or tilting your head down, depending on whether it's elevation or depression. Well, in the question, they say that the angle of depression of the beam is 70 degrees. That's here. Okay? That's our 70-degree angle. So that tells us a lot of things. And there's multiple ways of setting up this question. I'm going to set it up in a specific way. Okay? You might find another way. I mean, you could draw another right angle triangle over here now as well, and that would be 150. But looking at the inside values here, can you now tell me, and I'm going to put a little line on that angle just to separate it from the other two angles, okay? Can you tell me what that big red angle would be? I'll wait for an answer in chat. That's right. It would be 20 degrees because the full angle is 90, right, folks? So that red angle is this one right here. That's 20 degrees. And now I have a scenario in this big triangle here. Now I should probably label the triangle just so we're clearly understanding what sides we're working with. So often when you're dealing with any kind of triangle, instead of labeling things opposite, adjacent, hypotenuse, which are side lengths, we can label the angles instead. And angles are always labeled with capital letters in math. You can go clockwise or counterclockwise. It doesn't actually matter with a triangle, okay? So if I label these corners A, B, C, and I'm actually going to label this one here D, okay, right there. So we're talking about triangle ABC here, the bigger of the two right angle triangles in that picture. Inside that triangle, we now have an angle and a side length, and when you have an angle and a side length in a right angle triangle, that means you can solve for everything else using SOHCAHTOA. Now what about triangle ADC? It'd be really nice to have an angle in that triangle. And there's actually two different things that we could do here. So just curious, chat, could you tell me what the value of that angle is right there? The purple one, which is this one right here. That was a quick answer. Awesome. Yeah, because we know that the entire red angle is 20, but I told you that a sliver of that red angle was 5. So that means that the leftover has to be 15. So we know that this angle is 15 degrees here. Now, here's another thing that we could have considered. Is there a way of finding this corner angle here? Now, do you remember, I don't know if you can clearly see that yellow. I know it's not very bright, but I'm going to be erasing it in a second anyway. But do you remember your Z, F, and C patterns when it comes to parallel lines? When you have two parallel lines, these are called, oh gosh, I always forget what the actual words, alternate angles? I believe it's alternate angles. I always just call them Z angles, but alternate angles are the same. Well, there's a Z pattern right here. Oh, and I made a mistake. Oops, sorry. Okay, I haven't written anything down. My brain made a mistake, but I hadn't said it yet. There's a Z pattern right here, right? I was going to say that that yellow angle is 70 degrees, but it isn't. That yellow angle is 75 degrees. So there'd be a way of finding an angle with the Z pattern as well. Okay? So I'm just going to erase all that, though, because I do think that the other way was the better way. Oh, can I not erase more? There we go. All right. So we have enough now. We have an angle and a side length in both of our right angle triangles, the big right angle triangle ABC and the small right angle triangle ADC. Well, what is our plan of attack? And maybe I should have talked about our plan of attack right at the beginning. Yes, there are multiple ways. Chat was just suggesting there's another way of finding another angle in there. There are multiple ways of finding the angles. There's another Z pattern. In fact, we could have found this angle here. Okay, so there's multiple ways of getting the values that we need to be able to solve these two triangles to find our final answer of x. The key here is we need an angle and a side length. So however you find that angle and side length, as long as you have proper mathematical technique to do so, you're good to go. I kind of like, I'm going to switch colors here. I kind of like this one because both triangles look exactly the same. We have the same angle at the top, or not exactly the same, but similar, I guess is the word I'm looking for. We have the angle at the top here, and we have the side length in the same positions. So it just makes things a little bit nicer for me to, I don't know, I like that kind of organization. Yeah, so let's talk about our plan of attack. How are we going to calculate length x here? Well, isn't length x a piece of length BC? So x is length BD, and I'm going to use a segment notation. I hope everybody's okay with that. When you write two letters like that with a line above it, you don't technically even need the line above it, but usually you do for segments. So x is BD, which is this length right here. Isn't BD a piece of BC? Well, do we not have a way of calculating BC now? Yes, we do. Well, isn't BD just the entire length BC minus the length DC? And BC is this length, and DC is this length. And we have a way of calculating those two lengths now. So that's our plan of attack, right? We have enough information in those two triangles now to be able to calculate the lengths of BC and DC. And if we just subtract those two lengths, it'll give us the length we're looking for. Which I'm not going to do, because I've done 90% of the question for you at this point. Not that you're going to have this question in homework, but you'll have questions similar to it. So I don't want to give everything away, because I do want you to be able to think of some of the things yourself. But, I mean, for the first few, I want to discuss the main plan of attack, so that at least if you haven't seen trigonometry in a while, it starts to refresh your memory as to how to do these kinds of questions. Are there any questions? Are there any comments? Seeing none, let's move on to this question. find the length of the 35th parallel of latitude to the nearest 10 kilometers. Assume that the radius of the Earth is 6,380 kilometers. So luckily they gave us a picture of this so that we could understand what they meant. Now the word length of the 35th parallel is interesting because the Earth is a sphere, and we're talking about latitude and longitude here, so we're talking about the sphere of the Earth, right? So if you think of a sphere, wouldn't the latitude length actually be a circumference going all the way around the sphere? But that's not what they're asking here, okay? They're asking if you went directly through the Earth, what would be the length from one edge of the parallel of latitude to the other edge of the parallel latitude, okay? They gave us the radius. Now look at where the radius is. It's right here. Right? They gave us this angle. How are we going to find this length? And I mean, we've got to discuss this because we're working with right angle triangles only. So where would those right angle triangles go? Like, how would I draw the right angle triangle to help me out? And what a lot of students might think of doing is, well, what if I draw my right angle triangle here? But the problem with doing that is you've now complicated the question to the point where you actually wouldn't be able to solve it, because you can't use the 6380 as the length of the radius if you cut the radius by a little bit. Okay, but I mean, you've got to try, right? Sometimes you're going to try something, it's going to be wrong. You're just brainstorming ideas. But what if we move that line here? Isn't this length here, sorry, my mistake, isn't this length here still 6380? Because it's a radius, right? So this length is still 6380, but this is now a right angle triangle. If this is 35, can we not find that angle there? Which I'm sure somebody's already figured out. Yeah, so 90 minus 35, which is 55 degrees, as stated in chat. Okay. Now, what I like to do when I have a diagram that I'm trying to brainstorm my way through is at this point, or even a little bit sooner, I'll pull the triangle out of the picture just so that I have a slightly bigger representation of that, right? So like I said, we know that this is 6380 because that's still the radius of the Earth. We're assuming a spherical Earth and not an elliptoid Earth. We know that this angle here is 55 degrees. All right. Can we find this length here? And the answer is yes. We have an angle and a side length inside of a right angle triangle. In fact, it's the opposite and hypotenuse. So with opposite and hypotenuse, we can use so, find the question mark length. But then we'd have, and this is me going through the plan of attack, right? This is me planning what I'm going to do before I do the math. Once we know this length, what do we do to it to find the entire length? And I shouldn't have to wait, that's just doubling, right? So we now have solved this question. We just have to do the math attached to it. So I'm just going to add this in so that when I post the note, you have some reference to what we just discussed. But, you know, the hard part of this question isn't actually doing the math. The hard part is reading the question. And imagine for a second that I hadn't given you the picture. Okay, now that would require you to know what the word parallel of latitude means. I would probably have changed the question to say a cross-sectional area of the Earth instead of the Earth itself, because, again, the latitude actually is a circumference of, like, at that height. Technically not a circumference, but it's a circular distance around that height. So, which we could, I guess, technically calculate now if we wanted to, because if we now know the radius of this circle, we can do 2 pi r to find that circumference. Okay, which is maybe what they're asking here, and maybe I'm mistaken. I thought it was just that distance this way, but maybe now they actually want us to find the circle going around the Earth. I'm not actually sure. Luckily, this is in your textbook, so go ahead and check it out on page 269. Okay, let's move on. So another interesting style of question that you might start seeing are three-dimensional questions. So this is exactly another example, from your textbook. It says, rock pillars are interesting geological features found in several national parks in Ontario. Rock pillars found in rivers and lakes have been sculpted by wind and water. A geologist wanted to determine the height of a rock pillar in a river. The geologist set up a theodolite at sea and measured angle ACB to be 28.5 degrees. So looking at the picture, ACB, now when you're talking about an angle, sometimes they won't use just angle C, because angle C is actually two angles. It could be this angle or it could be this angle, okay? So saying ACB tells you exactly what triangle you're in and which angle we're talking about, which is this one right here. Now the problem with this is, can you visualize this as being a three-dimensional picture? The other thing is, what the heck is a theodolite? So I've heard the word theodolite used interchangeably with another word. I had to actually look it up because I hadn't heard the word theodolite in a long time. The word I usually hear is transit. Now a transit, if you've ever driven along the highway or driving in a car along the highway, seen workers out on the side of the highway with a tripod kind of looking thing, and they're often standing beside the tripod, leaning over, right, looking through it. That is a transit, and transits and theodolites are basically optical instruments that allow you to measure angles horizontally and vertically very, very precisely. So in civil engineering, when you're working on a road, you often have to know like the angles involved with the bank of the road and stuff like that. So they'll use those kinds of instruments to help. And I'm not exactly sure where else or why else they need them, but that's basically what a theodolite is. Okay. So again, you know, reading this word problem right away, if you got to that word and didn't know what it meant, it might throw you off a little bit. So we know that this angle ACB is 28.5 degrees. The baseline CD was marked off perpendicular to BC. So CD, which is here, is perpendicular to BC. And this is where that triangle right here is that they're talking, or that angle, I'm sorry, that they're talking about right there. If the height of the theodolite is 1.6 meters, so they're talking about this height here, is 1.6 meters. What is the height of the rock pillar to the nearest tenth of a meter? Oh, I forgot one thing. The length of CD is 10 meters. So we know this length here. I was wondering where that measurement was. Okay. So if I was to try to draw this picture off to the side, here's the problem. This angle does not look like a 90-degree angle, but it is. And it's because of perspective drawing in 3 dimensions that that looks like that, right? So you've got to be very careful when you're looking at diagrams that are in 3 dimensions. It's a lot easier to see it when you're looking at the actual picture that it's in 3 dimensions. But if you just look at that off to the side here, it's hard to tell that that is a right angle right there. Okay. Now, what is the goal of this question? The goal of this question is you can't swim out to the theodolite, climb it, and measure its height. But I want you to notice that none of the measurements taken here are taken from the side of where the theodolite is. It's all taken from the beach. As long as you had the transit or the theodolite. By the way, a little off topic, but your cell phones, there's an app you can get, and I'm forgetting the name of it, and I can't look it up right now, I'm sorry. But a tool that measures incline is a clinometer. And if you look up apps for either transit or clinometer, there's actually an app on your phone that when you tilt your head back and forth, it'll actually tell you the angle. And if you lay it flat on your palm of your hand and turn it, it'll tell you what angle horizontally you're turning your phone at. So we now have technology in our hands that can do pretty much the same job as a transit can. Okay? You can take all of those measurements from the beach. You don't even have to get to the pillar, and you can actually do the calculation of the height of the pillar. Now, one of the reasons I'm getting excited here is because when I was a physics teacher, and I don't know if your physics teachers at, I think they do at Llewellyn. You remember, I'm fairly new at Llewellyn, so I don't know how everything works, but I know for a fact that I used to bring my students to the Wonderland Physics Day, and oftentimes you'd have to calculate the height of roller coasters, and you could do it with this type of technique. You don't have to climb the roller coaster and measure downwards, which is not going to be allowed anyway. But if you take a few measurements on the ground, you can calculate the height of things you can't reach. Okay? So knowing that this is 56.4, oops, sorry about that. This is, I'm just going to draw it, I'm just going to write it off to the side. So this is 56.4 degrees, knowing that this is 28.5 degrees, is all we need to be able to find the missing height, which is this height here. Actually, I'm going to call it y because it's vertical, okay? And the key thing is this side right here. If we can find that side length, because it's a shared side for both triangles, once we find its length for the first triangle, we have its length for the second triangle as well. And it's just a matter of saying from 56.4 degrees, the red side here is the opposite. The 10 meters here is the adjacent, so I'd be using tan to find the red line. And once I know the red line's length, I can go into the second triangle and say from 28.5, the opposite is y, the adjacent is the red line. I've now calculated the red line, it's a tangent scenario again, and I can find y. Okay, so find the length of the shared side in triangle BDC. This is how you write triangle, actually be BCD if I follow alphabetical order, okay? In triangle BCD, then find the height. I know I labeled it Y, but it's actually AB. In triangle, well, let me redo that. And that would be triangle ABC. And that is our plan of attack. Okay. So I'm going through these again relatively quickly. I'm hoping that if you don't understand something, you're going to stop me and chat. But these are right angle triangles, and I think with me guiding you through the word puzzles of these word questions, I am hoping that that's going to be something that you'll be able to do. And these are in your textbook. The example above and example 5 are in your textbook, so you can go and look at their solutions while you're doing the homework tonight to help you out if you need it. Okay, I want to finish the lesson today with this question. It just happens to be the most difficult one of the bunch. I had at least one student tell me that they've seen similar questions to this before. This is what I would consider the hardest question for basic trigonometry. Again, that means not using sine law, not using cosine law. So I'm going to let me know if once we've done this question, if you've seen one like this before or not, okay? Now, there are questions that you may have seen last year that deal with two buildings side by side, and they actually tell you to find the height of the two buildings, but they give you the length between the two buildings. That is what I would call a quintessential trig question. This one's similar to that one, but it's got a little bit of a twist to it. So it says a communication tower is some distance from the base of a 70 meter tall building. So we know that the building itself is 70 meters tall. We do not know how far apart they are, so I'm going to call this length x, okay? And all they did is they translated this height of 70 meters over to this side of the picture, which would match. So this would also be that 70 meters, right? From the roof of the building, the angle of elevation to the top of the tower is 11.2 degrees. So yes, it's easy to see that here, but imagine had I not given you the picture, would you have been able to draw that angle of elevation from the top of the building? From the base of the building, so going down to the base of the building, the angle of elevation to the top of the tower is 33.4 degrees. Determine the height of the tower and how far it is from the base of the building. Round your answers to the nearest meter. So here's the problem with this question. They didn't tell us any length in either of the right angle triangles. So which right angle triangles am I talking about? If I label this one A, B, C, so this top triangle here is a right angle triangle. And then from A, if I go down and label this D and E, we have another right angle triangle at ADE. Okay, there's another right angle triangle here, but that one's not going to help us much. Because it's cut off right here. Now, had I allowed you to use sine law and cosine law, maybe that triangle would come into play, but it isn't going to come into play with what we're doing here. So we have two triangles, okay? We have triangle ABC, that is a right angle triangle, and we have triangle ADE, which is also a right angle triangle. Okay, so these are my symbols for right angles here. All right, so we need a plan of attack. What am I trying to do in the end? I'm trying to find this height here, which I'm going to actually call capital H. Okay, so we're looking for capital H. Great. There's one more length that we're going to need, and I'm going to label that length in red right here. And I'm going to label that length Y. All right, now why do we need length Y? We need length Y because it's a length in the first right angle triangle ABC that I was talking about. Okay? Now, if you've never seen a question like this before, I don't know how long it would take a student to actually figure out what I'm about to show you. So normally I would give you a little bit of time to like think it over and see if you could come up with a plan of attack, but because of the long distance learning here and because I don't want to take too much time, I'm just going to guide you through this first one, and it may be review for those of you who might have seen it before, but it might be brand new for others. So, and even if it is review, I think it's definitely worth doing simply because of all the stuff that's going to go on here. Okay, so we're going to work in two triangles. Let's do triangle ABC first, so the little tiny one at the top. Look at the angle that they gave us. Okay, which side is this side AC, which also contains my Y, by the way, with respect to 11.2. So what I'm asking you here is, following SOHCAHTOA, which side is y? Is it opposite, adjacent, or hypotenuse? And I'm hoping everybody can see it's the opposite side. What other side length? We're not given as a number, but we are given as a length. Well, we're also given this x value. Now, do you all see that that x value is also this length in triangle ABC? So what I'm getting at here is there are shared values in both triangles. Little x is a shared value. It's not a shared side, okay? It's not the same as the one we just did, but it is a shared value. Both of them have a length of x in it, so that's going to come into play in a second. So let's work with that x, okay? So I'm going to use red because red's going to contain the y that I'm talking about here. So in triangle ABC, we have an opposite side, little y, and we have this side x, which is the adjacent side. And that means I can write tan 11.2 is equal to the opposite side y divided by the adjacent side x. Now let's look at triangle ADE, which is this big triangle here, and look at the angle that they gave us in ADE. They gave us angle 33.4. Now, if I go across the triangle from 33.4, that gives me big H as the opposite side of angle 33.4. However, I'm not looking for big H. I am looking for big H in the end, but I can't find big H if I don't know little y. Okay? So instead of using big H as the opposite side, what is this full length here? Isn't it y plus 70? So I'm going to use purple for that. So we've got tan 33.4, oops, sorry about that, is equal to y plus 70 all divided by x. And this is why this question is so complicated, because you cannot solve it using just one trigonometric equation of SOHCAHTOA. You actually have to use two separate equations. Why? I wonder if anybody knows, why do we have to use two separate equations? Now they're separate for now, they won't be separate for long, but why do we need two equations? Exactly. So somebody in chat just said because there are two variables. Okay? As soon as you have two unknowns, you need two equations to be able to solve for those two unknowns, which is very similar to grade 10 solving linear systems of equations again. If you have two equations, x plus 3y equals 7 and 4x minus 7y equals 9, you need two equations because you have two unknowns, x and y, and that's very similar to what we have here. And therefore, we're going to use a very similar way of solving this question. Okay? Here's what we're going to do. Let's isolate y in both equations. Why am I choosing y? Because the variable y is extremely easy to isolate in this equation here. We just have to move the x over to the other side. Over here, it's a little bit trickier. I'm going to move the x over to the other side again. Now, while I'm doing this, can I get an idea in chat as to how many students have done this question before? And if you're also willing to tell me if you've never seen this question before, that'd be great. Has anybody never done this before? Or doesn't remember it? Okay, I'm not getting any other responses, so that means some of you have done it before. I'm assuming some of you don't remember it, though. But like I said at the beginning, whether you've done it before or not, I still think it's good to see it, because that idea of having two unknowns happens fairly regularly from now on in math. And therefore, you need to always be aware that if you have two unknowns that are participating in your equations, you're going to need two equations to solve it. And to think of that on your own can sometimes be a little bit difficult if you just haven't reviewed it for a long time. Okay? So what are we going to do next? Well, first of all, I'm not quite done isolating the y here, so I've still got one more step. I've got to bring the plus 70 over to the other side. So I'm going to have x, oops, wrong color. So I'm going to subtract the 70, I'm going to get that. Now, two equations, two unknowns. There are two different ways of solving that style of a system. We can either use the substitution method or we can use the elimination method. Well, because I've isolated both y's, it's actually better to use the substitution method in this case. So what we're going to do is we're going to take x tan 11.2 and we're going to substitute it into the y of the second equation. Basically following the same idea as linear systems of equations from grade 10. So the issue now becomes, notice that I only have one variable left, first of all. That's the whole reason we did that, is to end up with one variable, which we can now isolate. How do I get x all by itself? So we're dealing with algebra now, right? So when you have x's on both sides of an equal sign, that is a bad thing. We always want to get all of our x's to the same side. So we're going to take the term that x is involved with and bring it over there. And at the exact same time, we're going to bring the minus 70 onto that side. So we're going to have x times tan 33.4 minus x times tan 11.2 equals 70. So I just took the x tan 11.2 and brought it over to the left-hand side and brought the 70 over to the right-hand side. You could do what was suggested in chat. I don't want to do that, because if I do that, I'm going to end up with some ugly decimals right at the beginning, and it's technically not going to be considered the best way of doing it, and I'll tell you why. Because in math later on, you're not going to have numbers. You're going to have variables for your angles. Okay? You wouldn't be able to divide by tan theta 2 as nicely as you could if it's a numerical value. So I'd rather do it another way. Once I've brought my x's, now I want you to think about this. If this was 2x, actually that's not going to work. Never mind. Forget what I was about to say, because it doesn't make any sense in this context. What could we do to get x out of these two terms now? What can we do to get x out of those two terms? Not yet. I don't want to simplify tan yet. There's another word I'm looking for. If I had x times a minus x times b, how could I get the x's out of those two terms? Correct. We want to factor this. We're going to pull that x out of both of those. Like so. And then I'm going to divide that ugly tan bracket on this side. Like so. And that'll give me my x value. And once I know my x value, I can come back up here, sub that x value into either of the two equations that I had. This one's much easier. That'll give me my y value. And once I know my y value, I can calculate my h value by coming back up here and realizing that h is just 70 plus y. And now you know why I consider that to be the hardest basic trigonometry question. And that's going to be it for today's lesson. So, I'll be probably assigning a few word problem questions from your textbook as homework tonight, folks. What you should also do is complete this question. Oh, I may have forgotten to post attendance. I'm sorry, I'll go do that right away after this lesson. I'm going to stop recording, so ciao everyone for the recording.